Hello and welcome back to rigid body mechanics again. Here we have angular acceleration, tangential acceleration, the two essential accelerations you should learn. First of all, let's review the map we developed in circular motion. We learned that if the object travels on the circle from point A to the point B, there is an angle subtended through which the object travels. This is theta, angular displacement. It's usually measured in radians, okay? And then we have a rate of change of theta. How fast or how slow the theta changes. It is angular velocity in vector language or simply angular speed if you don't care about the direction. How to find omega? It's very easy. Omega is supposed to be theta divided by t. Rate of change of theta it's measured in radian per second. If you're going to go back from omega to theta, it's very easy. Theta is supposed to be omega times t. If omega is constant, instantaneous, and average omega will be the same. Otherwise, you should apply omega bar, average omega. That's all. So going rightward, division by t, leftward, multiplying by t. Anyway, there is an object here. It's moving on the circle from point A to the point B. Basically, it has a speed, it has a distance traveled. Distance traveled means the length of this arc from here to here, length of this arc. How to find it? We had an elevator. This elevator is r. If you are going to find the s, the distance traveled on the circle, you should just simply multiply theta by r. So s is supposed to be r theta, provided r is necessarily measured in radians, but r is arbitrary. It could be in centimeters, so you will find s in centimeter. If you take maybe the other SI unit, for example, meter, it will be in meter. It's okay, but theta must be necessarily in radian. Anyway, we have also a big brother or little brother for omega. What's that? It's the linear speed. Linear speed is v. How to find it? Same elevator. V is supposed to be r omega. Here omega is measured in radian per second, and if r is maybe plugged in for meter or whatever, it will be meter, it will be meter per second, centimeter per second. It's very easy. But omega necessarily in radian per second. How to correlate S and V? It's very easy. Again, the same thing. Division by T will give you V. So V also is supposed to be S over T. And if you go back, you should multiply by T. So basically S is V times T. That's all. This is the map we developed in circular motion, and I just wanted to review that. Now let's proceed to the next one. Next one is a very important introduction. Uniform circular motion. What is uniform circular motion? Suppose that this object is moving on the circle, but at a constant rate. Means that it travels, for example, 10 degrees in each second. So in each second, we expect 10 degrees of angular displacement. A question: does the object travel through equal angles in equal time intervals? The answer is yes, because this is uniform circular motion. So it won't have any speeding up or slowing down motion. The speed, or let's say the velocity in vector language of this object, will have a constant size. Means that the value of velocity, the magnitude of velocity, which is the speed, is always the same. Let's say this is 10 meters per second. It will keep the same value all along its motion. This is why we call it uniform circular motion. Question number 2. Does the object have acceleration? Yes, it does. To which direction? Okay, the only acceleration you can have, we learned it already, is the centripetal acceleration. Centripetal acceleration can be found as v squared over r or r omega squared. We already passed this lesson in circular motion. You learned it. If you want, you can have a review again. The link is available. Now let's proceed to the other one, non-uniform circular motion. Non-uniform circular motion means that speed is changing. Let's say it's moving at a speed of 10 meters per second, and in the next second it goes to 12 meters per second. So it's speeding up. Or also it can slow down. Anyway, the speed is not constant. So there is no guarantee for the theta to be the same in the upcoming same time interval. What does it mean? Question asks me, does the object travel through equal angles in equal time intervals? Not necessarily. No. It may travel for 10 degrees in 1 second, and the upcoming 1 second it may be 20 degrees. Question number 2. Does the object have acceleration to which direction? Oh, of course it does. It's very challenging. As it's speeding up or slowing down, rather than the centripetal acceleration, also it has an acceleration which is called angular acceleration, and also the tangential acceleration, the topic of this video. What is that? This is the centripetal acceleration. You are familiar with that. We learned it. The other is the tangential acceleration, an acceleration tangent to the circle. It could be toward the direction of motion. Let's say the velocity is rightward. So it's speeding up, or we can take the velocity leftward at this point. So the tangential acceleration will slow down the motion. It is exactly the linear acceleration. We learned it in the linear motion. Now we are correlating that with the circular motion. Tangential acceleration is measured in meter per second square. Okay. The other also is the rate at which the angular speed is changing. It's actually alpha. Alpha is angular acceleration. Alpha is supposed to be rate of change of omega. How omega changes. That's very essential quantity, and we should learn them. And also we will correlate alpha and tangential acceleration in this video. Okay, let's start from the scratch. Angular acceleration. The rate of change of angular velocity, I mean omega, is called angular acceleration. In general, basically, we can suppose that at time t1, the object has initial angular speed like omega 1. At the other moment, it could be omega 2. So at t2, it's omega 2. And necessarily, it must be different. Otherwise, we won't have any angular acceleration. So omega 2 is different from omega 1. It could be smaller or larger, depending on a speeding up or slowing down motion. How to define it, as I told you, is rate of change. So it should be delta omega over delta t. So let's define it like that, delta omega over delta t, or in detail, omega 2 minus omega 1 in extended form divided by t2 minus t1. It's measured in radian per second square. This is average alpha. Actually, this is average angular acceleration. But as usually in these type of learning, we are working with constant alpha. If alpha is constant, means that the rate of change of omega won't change in future. We can say alpha bar and alpha instantaneous and average alpha are the same. So forget about the change in alpha. For the time being, let's make it simple. Anyway, this definition is definition of average alpha, average angular acceleration. Now let's go to the next one to learn tangential acceleration. Tangential acceleration is actually the linear acceleration, I told you. But how to relate tangential acceleration and actually the angular acceleration? It's very easy. Look at this. Tangential acceleration, I told you, is a vector tangent to the circle. Depending on the direction of motion, it could be speeding up or slowing down acceleration. If the velocity has the same direction as tangential acceleration, it's a speeding up. Otherwise, it's slowing down. It's not that important anyway. It is tangent to the circle. Meter per second square. The unit is the usual unit we use in linear motion. Actually, now our goal is how to relate this tangential acceleration to the angular acceleration. Tangential acceleration is defined as usual, delta v over delta t, change in velocity over change in time. rate of change of velocity. Forget about the vector properties of the velocity for the time being. So let's say change of speed in every second. Now we can develop that. Here, velocity, we learn that the speed, we learn that is r omega. V is r omega through the elevator. I introduced and I reviewed this session. So as the radius of the circle is assumed to be constant, we can take it out of delta. So it's r delta omega over delta t. Change in omega in every second was introduced in the previous slide. It is alpha, so it's supposed to be r alpha. Interesting, this elevator can take us from the orbital motion, from the circular motion, again to the linear motion. What does it mean? Let's develop our map again. You remember, I told you we have angular displacement theta, we have angular speed omega, and we have also angular acceleration now. Very good. How to relate them? It's very easy. Dividing by t will take you from the left to the right. For example, omega is delta theta over delta t, or simply theta over t. Alpha is delta omega over delta t, or simply omega over t. Go to the left, you should multiply. Means that omega is supposed to be r alpha and theta is supposed to be r omega in general. Okay? And let's use the elevator. The elevator takes us from the orbital motion, circular motion to the linear motion. As I told you, S must be r theta, same map. V must be a vector tangent to the circle, and the magnitude is r omega using the same elevator. And now we have tangential acceleration. Using the same elevator, we have tangential acceleration to be r alpha. Again, tangential acceleration is a vector, I just emphasize, is a vector tangent to the circle. Just I should remind you, we have another acceleration we learned in circular motion necessarily always exists, regardless if the motion is uniform or non-uniform, it's not that important. And it's v squared over r, or r omega squared. Centripetal acceleration, which is a vector toward the center. Okay, let's consider this question to learn more. A bicycle is placed on a repair stand and a mechanic spins its rear wheel from rest to a final angular frequency of 240 revolutions per minute in a time of 4 seconds. Part A, calculate the angular acceleration of the wheel, angular acceleration alpha, in radian per second squared, assuming that it is constant. Okay, let's say it's a constant angular acceleration. Okay, how to find it? Basically, angular acceleration is delta omega over delta t. In question, I see that it starts from rest, so omega 1 is 0. But what the omega 2 is? Omega 2 is a little bit weird. It's 240 revolutions per minute. Omega normally is not reported like that. So let's find it like this. This omega is delta theta over delta t. You know, each revolution means 2 pi of angle. You go around the circle, 2 pi. Okay, so 240 revolutions means 240 times 2 pi. This is the total theta. So theta over t, or delta theta over t, must be 240 multiplied by 2 pi divided by SI unit of time, 60 seconds, because it's minute. Okay, it's 25 radians per second. As I mentioned, omega 1 starting from rest is supposed to be 0, so the answer is 25 divided by 4. That's 6.3 radian per second squared. And this is constant alpha because it has a constant rate mentioned here. Next part of the question, the radius of the wheel is given to be 34 centimeter. Calculate the final linear speed of the point of a point on the circumference of the wheel. Let's say this is the wheel and this is a point on the wheel, point M. We are gonna find the final linear speed V. Okay, normally V is r omega and it starts from rest. So V naught, initial velocity, initial speed is 0. But final speed depends on final omega. So let's use final omega according to what we found in the previous slide. Final omega, you see it's 25 radian per second. And so it's 25. and R must be in SI units. We need SI unit here. So it's 0.34 in meters. It's 8.5 meter per second. If you use 34 in centimeter multiplied by 25, it's not that important. Anyway, the answer will be in centimeter per second. Anyway, part C, outline how the centripetal and tangential accelerations of the point on the circumference of the wheel vary with time. First, centripetal acceleration. You know centripetal acceleration is r omega square. Anyway, we know that the object or the point is a point at this specific definite distance to the center. So radius won't change. But omega is changing. Anyway, omega starts from rest, goes to a high value, maximum value, whatever it is. So increasing omega will raise the right side. So centripetal acceleration for this point will increase. But about the tangential acceleration, no, it won't change. Radius is 0.34, okay? And alpha 6.3. We found it in the previous slide. So it's constant. No, it won't change. So centripetal acceleration will increase, but tangential acceleration, as angular acceleration is considered to be a constant value, won't change. Okay, thank you for attention. Hope that this video is useful for you. Please review the concept, and again, thank you for being with me. I'm waiting to see you in the next video. Goodbye.